Hi guys. So in this video now let us see how to find the electric potential for a single charge and for different charge configurations, right? So till now we have talked about electric potential in terms of conceptually what it means. Now let's start actually putting a number to it. So let's start with the simplest possible case. So let's say you have a charge plus Q, right? And you want to find the electric potential at a particular point, which is, let us say, at a distance r from this particular charge. Right? Now we have done discussions and we've come to this conclusion that the potential Vr, right, this is nothing but minus integral E dot dr, right, where the and r is a position vector, where this goes from some reference point, some reference point, r goes from r reference point to the r where it is right now. Right? So this is the definition of, or this is how we are defining electric potential, right? Okay. Now normally, as you know, the reference point is taken at infinity. So I'll rewrite this as, so if, let's say, if reference point, right, if reference is at infinity, then in that case we'll say potential at r would be equal to nothing but minus integral E dot dr, right, from infinity, where r goes from infinity to the current position vector r. This is going to be my electric potential. Okay, so now let's evaluate this for this particular case, right? So what is this going to be? So let's do this. So now E dot dr. Now let's do one thing. Let's this is where the charge is. Now let's assume that this charge goes, this dr is nothing but it's along this line, it is from here to here, right? So this distance is dr, right? If I were to write this as vectors, I would say r is this vector, this is r, right? And this vector is dr, and r plus dr would be this arrow, right? R vector plus dr vector would be this arrow from here to this point. And I'm taking dr as along the same direction as r, right? So for this small, just look at this small element. So for this we would have E dot dr, right, would be equal to electric field into dr, the magnitude, into cos of theta, cos of angle between them. Now as you can see here, this is direction, this is my dr, and my electric field would be in what direction? Just go back to Coulomb's law, right? So if this is the charge, right, if I put a unit charge here, the force would be in this direction. Force would be along the line joining this charge, the test charge, and plus q. So that would be along the radius. So my electric field also would be in the same direction. So angle between them is going to be 0. So theta here is 0, right? And what is cos of 0? So theta is equal to 0, and therefore cos of theta is equal to 1. And now I can say that E dot dr vector, right, is equal to E into dr. They look the same, but do not take it for granted. So here E dot dr, these are vectors and this is a cross product. Here this is just a multiple of two magnitudes, two scalar quantities. Okay. So now that I have this, now let me go back and go to this equation here, right? This is my equation 1, and now let's do this. So we say Vr equals minus integral, right, E dot dr, no sorry, not E into dr, this is not dot product, these are two scalar quantities, and where r goes from infinity to r, right? Now why here we said we are moving the charge from this point to this point, we are giving it a dr displacement, right? Normally, so when we say dr, d of anything, it means a small increase in that number, right? But it doesn't mean the charge has to move from here. Charge can move in any direction. So that is shown by the unit. So the initial, in the integral, this limit is telling me the initial point, this is telling the final point. Okay? So now we can say that this is, and what is my electric field E? E is going to be nothing but kq upon r square, right? So this would be minus integral infinity to r k q upon r square into dr K and Q are constant, so we'll get it out as coefficients. So we'll say minus KQ, right? And this would be integral of 1 upon r square into dr from infinity to r. Now what is integral of 1 upon r square? That would be, so this is r to the power minus 2, so that would basically be r to the power minus 2 plus 1 upon minus 2 plus 1, which means this would be nothing but minus kq, right? And the integral would be r to the power minus 2 plus 1 divided by minus 2 plus 1. I am just writing the steps so you are absolutely clear as to how we are doing this, right? And this would evaluate to minus 1 upon r. And there is a minus sign here as well, right? So this would be minus kq, right, into minus 1 upon r, right, from infinity to r. And now if you put the values, basically this would be minus kq into minus 1 upon r plus, which is minus of minus, so plus 1 upon infinity, right? This is minus of minus 1 upon infinity, which is plus 1 upon infinity. This number 1 upon infinity is nothing but 0. And so what is left is minus 1 upon r, and there is a minus sign here, so it will just become V, the potential at distance r would be nothing but simply kq upon r. That's it, right? Compare with electric field was kq upon r square, the magnitude, and then it had a direction. The direction was along the radius. So it would be kq upon r square. Electric field would be kq upon r square into a unit vector which is along the radius. So this result, let me write this here somewhere so we can see this carefully. Okay, so we'll say, so potential at r is equal to kq upon r. Very, very simple and a very beautiful result, right? So now this is a big deal, right? But you might say, okay, but this is like a very, very simple case, so why don't we take something more realistic? And I will say, yes, you are right. This is a very simplistic case. So now let's say, what if, the question obviously is, what if there are multiple charges, right? No problem. So let's say instead of 1 q, now let's say there are, here I'll just draw and show you. Let's say there is a q1, there is a q2, there is a q3, right? And there could be like lots and lots of charges. Right? Now let's say if you want to find electric field at a particular position, right? How would you do that? So I would say, let's see. So let's go and revisit this, right? So whenever we get a question which we kind of, we're going to the next level, let's go back to basics and start from this. So basic concept is this, right? And when we take the reference point is infinity, and this is my basic concept. So we'll say, okay, no problem. So for this multiple charge configuration, I'll just say my potential at r is nothing but minus integral E dot dr, right? And this is from infinity to r. Now what is E? E is the electric field. Electric field because of what? Electric field because of all these charges. But then each one of them is exerting electric field independently. So we'll say, okay, so the total electric field here E would be what? This would be vector sum of. This would be vector sum of electric field due to this charge, this charge, this charge, and so on and so forth. Right? Now let's say E is what? E is the electric field which is equal to electric field E1 vector plus E2 vector plus E3 vector and so on. And each E1 vector is the electric field caused by charge Q1. E2 is the electric field caused by charge Q2 and so on. Let me give one example. So let's say if I take this point, this charge will exert a field in this direction. Q3 as an example would exert a field in this direction. If I just take Q1 and Q2, then if these are two electric fields, then the net electric field due to these two would be using parallelogram law, it would be this particular field. Similarly, we have to add this one. So this is the way to think about it, right? So here in this integral, which is the electric field? It is this electric field. This is the field that we are talking about here, okay? Which is nothing but vector sum of each of the fields caused by each of the charges. Now we can say that V of r is equal to minus integral E dot dr, and what is E? E is E1 plus E2. So now I'll write this as E1 vector plus E2 vector and so on, right? Dot dr, where r goes from infinity to r. And now I can break it into, I can take each of them as separate terms. I can say this is equal to minus integral infinity to r E1 dot dr minus integral E2 dot dr, right, again infinity to r, and so on, right, and so on. Now, what is this? This is nothing but potential due to charge 1, independently due to charge 1. This is the potential due to charge 2, right. So now we get a very simple result, which is kind of very intuitive as well. So V at r, the potential at a particular point, is equal to V1 plus V2. In fact, if you want, you can say V1R plus V2R plus V3R and so on. And what is telling us? It is telling us that electric potential at a point due to multiple charges is equal to the sum of electric potentials due to each individual charge, right. Now, let me give you the intuition behind. What's the intuition? Intuition is the following. If I have to take an object from infinity to this particular point, I have to do some work. The total work done to take 1 unit charge from infinity to this particular point is equal to the work done by me if only this charge was there, plus the work done by me if only Q2 were there, plus work done by me if only Q3 charge were there, and so on, right. So each of those would be the electric potential for each one of them, and this is the total potential. So this is very simple looking, but a very, very powerful result. So this is what we are going to use conceptually when we talk about potential due to a charge distribution. So there again we'll think about the charge distribution as a combination, as a sum of a lot of small element charges, and then we'll find the potential due to each one of them and add it up, right. So this is the basis behind that. Thank you very much.